Good evening. I take on 2012 data question. Remember, I want to clear the data questions from 201 to 2016, and then from there I can maybe start from 200 going up to 1989. So I welcome you to my data question, and let's see the details. So KCSE 2012 Biology Paper 2, Mastering Data Interpretation with an Expert Examiner. Already you have a hint of what the question is all about, because what you see there, what can you see there if you are asked? Can you see a lizard and a snake? What relationship do the lizard and the snake have? More from the video. Understanding predator-prey relationship is crucial for wildlife managers and conservationists when trying to restore or maintain healthy ecosystem. By analyzing population trends, they can determine when predator or prey populations are out of balance and take action to prevent species decline or overpopulation. For example, in wildlife reserves like Kenya's Masai Mara, the predator-prey balance between lions, predators, and herbivores like wild beasts prey is constantly monitored to ensure ecosystem stability. Conservationists use this data to protect both species. Type of biotic relationship. Predation. This is a relationship where one organism, the predator or the snake, feeds on another, the prey, the lizard. The lizard will have the least biomass. In the food chain, biomass decreases as you move up trophic levels. Since the lizard is the prey and the snake is the predator, the lizard occupies a lower trophic level and will have less biomass compared to the snake, which is higher in the food chain. Concept of survival for the fittest. Guys, we are just having these things as an introduction. Survival of the fittest means that in a predator-prey relationship, the organisms best adapted to their environment are more likely to survive. In this case, the snake will survive if it is able to successfully catch and overpower the lizard, while the lizard will survive if it can escape or evade the predator. Both species have developed physical and behavioral traits that enhance survival, but only the fittest individuals will live to reproduce and pass on their genes. 3 visible survival features for the organisms. Camouflage. Both snake and lizard, both animals may exhibit colors or patterns that blend with their environment. helping the snake to ambush, play, and reason to avoid detection. Speed and agility, lizard. The lizard may be equipped with speed and agility, allowing it to quickly escape from predators like the snake. Vermin or constriction, snake. The snake may use vermin if venomous or constriction if a constrictor as a hunting mechanism to overpower the prey. Now here comes to the task of 2012 data question. The data provided below represents population of a predator and its prey over a 50 years period. So you can see time in years, then you can see population in relative numbers, then you can see population of P, population of Q. Using same axis, draw graphs of the relative populations of P and Q against time. Okay, so we are supposed to use the same axis to draw the graph of the relative populations P and Q against time. As the grid. With a reason, identify the curve that represents the prey. Roman 3, account for the two populations between 25 and 32 years. Roman 4, which years were the two populations equal? And Roman 5, apart from predation, state 3 biotic factors that may have led to the decline of the prey population. B. Describe the hazards of air pollution by sulfur 4 oxide. If you have ever felt confused about where to start with graphing or struggled to present your data clearly, this part of the video is for you. I will take you from the basics to the finer points, ensuring that you feel prepared and ready to tackle any biology experiment with confidence. Step-by-step guide to drawing graphs. Create a table of values. From the data provided, make sure you list the time in years in one column and the corresponding population values of P and Q in separate columns. Choose an appropriate scale, number 2, x-axis time in years. Since the time values range from 5 to 50 years, select a scale that allows you to plot the time intervals accurately, e.g. intervals of 5 years. Y-axis population. Look at the maximum population values for P at 4,000, for Q at 3,000. Choose a y-axis scale that accommodates both populations and allows you to see variations, e.g. intervals of 2,500 or 5,000. 3. Label the axis. On the x-axis, label it as time in years. On the y-axis, label it as population. Also, give the graph a title such as population of P and Q over time. 4. Plot the points for population P. For each time value, locate the corresponding population of P on the y-axis. Plot a point where these two values intersect Time on x-axis, population on y-axis. Example, at 5 years, population of P is 24,500. Plot a point accordingly. Number 5, plot the points for population Q. Repeat the same process for population Q. Example, at 5 years, population of Q is 17,000. Plot a point accordingly. 6, connect the points. For population P, connect the plotted points using a smooth line or a straight line segment to show the trend over time. For population Q, do the same using different style, e.g. dashed or different colored line to distinguish between the two populations. But we recommend you use maybe a different color, but not dashed. Include arranged. Since you have two different populations plotted on the same graph, and arranged data identifies which line represents population Q and which represents population P and which represents population Q. You can use different colors of symbols, like a circle for P and an X for Q. Arranged is a key. Review the graph. Make sure all the points are plotted accurately and that the lines are drawn smoothly to represent the population changes over time. Ensure the axes are labeled, the graph is titled, and the legend is clear. By following these steps, you'll be able to accurately represent the population trends of P and Q over time on the same graph. The graph. Here is the graph of the relative population of P and Q over a 50-year period. Using the provided data, population P, blue line, and population Q, red line, have been plotted against time in years, showing their fluctuations over time. Population P generally increases with peaks at years 15 and 20, followed by a decline and then a rise towards year 50. Population Q increases, peak at 25, followed by a slight decline, and then a gradual rise towards the end of the period. This graphical representation should help you analyzing the data play dynamics over time. So let's go to the graph and see what we have said here. Welcome. Graph of the relative population of P and Q against time. You can see population in relative numbers. You can see these dashed lines at okay, we will see the mark, this mark, because one small square represents what? 0.5. So two small squares represent 1. And here I can see how many small squares. 1, 2, 3, 4. 4 times 0.5, that is 2. So this should be 22 years. And here we have 39 years is when the populations are equal. And this generated in graph, you can see the same. Okay. All right. The blue P, the red Q. With a reason, identify the curve that represents play, 2 marks. P represents the play. Prey population is initially higher. Play population usually starts falling earlier. Account for 2 populations between 25 and 32 years. Both populations decrease because play is not enough to sustain predator population, or environmental stress limit population of play. Which years were the 2 populations equal? 23 plus or minus 0.5, as I've shown you, and 39 plus or minus 0.5. So it ranges between 22.5 to 23.5 and 38.5 to 39.5. The curve representing the play is one for population Q rent curve. Reason: play populations typically experience rapid growth when predator numbers are lower, as seen in the rise from year 5 to 25. Play populations also tend to reach higher numbers than predators, followed by a decrease as predator population increases, leading to more predation. Between 25 and 32 years, the population of P predators decline after year 25 from 31,000 to 25,000 by year 35 due to lack of sufficient play, as the play population also begins to decline. The population of Q play declines steadily from 33,000 to 30,000, likely due to high predation pressure from the predator population that was higher in higher years, 25 to 25 years. The 2 populations were equal in year 35 when both P and Q had a population of 30,000. 3 biotic factors that may lead to the decline of prey population: competition for food or resources with other species, diseases or parasites that may have infected the prey, lack of shelter or breeding place due to competition from other organisms, or habitat destruction. Apart from predation, state 3 biotic factors that may have led to the decline of prey population. These ones are less food for prey, competition for food, competition for space, mate or shelter, immigration or prey. Accept migration to another habitat, not migration alone. Diseases, death of prey, human activities, culling or poaching, hunting, deforestation, transpiration of animals, pollution, and finally, parasitism. Accept parasites. Mark first 3. Describe hazards of air pollution by sulfur dioxide. Sulfur dioxide in the air causes respiratory diseases, e.g. bronchitis, pneumonia, aggravates asthma, emphysema, forms acid rain, which lowers soil pH, corrodes metals or building. Accept machines, metals, stones, sculptures, statues, etc. Acid rain poisons, drainage, kills plants, animals, chlorosis. Sulfur dioxide in higher concentration of the gas, it kills human or damage plants. Acid rain causes the leaching of magnesium or calcium or aluminium. Accept the symbols in aqueous form, as you are seeing here. Calcium aqueous, magnesium aqueous, aluminium aqueous. Now, from the computer, we have, or from ChatGPT, hazards of air pollution by sulfur oxide, respiratory problem. Sulfur dioxide can irritate the respiratory system, leading to conditions like bronchitis, asthma attacks, and other lung drugs. So these points are the same as the ones which were given there for the marking of KCSE, but expounded. Acid rain formation. Sulfur dioxide contributes to acid rain when it combines with water vapor in the atmosphere, leading to damage to buildings, crops, and aquatic ecosystems. Eye and skin irritation. Direct exposure to sulfur dioxide can cause eye irritation and skin problems. Environmental damage. Sulfur dioxide negatively impacts plant growth and can damage ecosystems, particularly forests, by affecting soil chemistry and plant growth. Real-life application. The information in this predator-prey population dynamics question has real-life application in various fields, such as 1. Wildlife conservation and management. Understanding predator-prey relationship is crucial for wildlife managers and conservationists when trying to restore or maintain healthy ecosystems. By analyzing population trends, they can determine when predator or prey populations are out of balance and take action to prevent species decline or overpopulation. Example, in wildlife reserves like Kenya, Masai Mara, the predator-prey balance between lions and herbivores is constantly monitored to ensure ecosystem stability. Conservationists use this data to protect the species. Agriculture and pest control. Farmers can apply predator-prey principle to biological pest control where natural predators like ladybugs are introduced to control pest populations like aphids instead of using chemical pesticides. Example, integrated pest management in crop farming leverages natural predators to keep harmful insect populations in check, reducing the need for harmful chemicals, and promoting sustainable agriculture. Epidemiology, disease control. Similar principles are applied in disease ecology where the population of hosts, prey, and vector predators are studied. In infectious diseases, understanding how a pathogen predator spreads through a host population prey helps epidemiologists predict and control disease outbreaks. For example, malaria control programs often study the relationship between mosquito populations, vector or predator, and human population, host or prey, to manage the spread of the disease. Environmental impact assessment. The study of population trends is important in predicting how changes in the environment, deforestation, pollution affect wildlife. This information can help governments and organizations make informed decisions to minimize negative impacts on ecosystems. Example, when planning construction projects or new infrastructure in wildlife areas, an environmental assessment considers the impact on predator-prey relationship to avoid ecosystem collapse. In this real-life application, understanding predator-prey dynamics helps to maintain biodiversity, promote sustainability, and mitigate negative impacts on the environment and human activities. In this video, we have explored the predator-prey relationship by analyzing the population data of two species over a 50-year period. We plotted their population changes on a graph, discussed the reasons behind the fluctuations, and identified key moments where their numbers were equal. We also explored real-world application of this knowledge from wildlife conservation to agriculture and disease. Now that you have seen how plane dynamics work? Can you think of other real-world examples where these relationships play a critical role? Share in the comments how this concept could apply to ecosystems, farming, or even human activities. And don't forget to hit the like and the like button and subscribe for more biology insights. Goodbye. Special thanks to ChatGPT, people who inspired me, family members, and all my teammates when marking exercise was going on. Bye-bye, guys, and see you next time for another video.